The universe as we know it now is a very structured universe. There's galaxies, there's stars, but it has not always been like that. We would like to study the period that formed the universe that we can see now. We can see the light that was emitted billions and billions of years ago, only at the lowest frequencies. So we need a low-frequency instrument. LOFAR is a low-frequency radio telescope, and it's actually the world's largest radio telescope.
LOFAR is a giant network of radio antennas spread across 8 European countries, built by Astron in the Netherlands early in this millennium to catalogue some of the objects in the early universe at the lowest radio frequencies.
We have the low-frequency antennas ranging between 10 and 80 megahertz, and high-band antennas between 110 and 260 megahertz. Every station of LOFAR consists of many of those antennas.
What makes LOFAR absolutely unique compared to previous generations of radio telescopes is that it has a very large number of simple, lightweight antennas, and all of the smarts is in computing.
Every antenna of LOFAR is sensitive to the whole visible sky. We add the data of all the antennas in software. By making use of the geometric delay, we can actually steer the beam of all these antennas to point to a certain direction in the sky.
Because LOFAR is a software telescope, you actually have the ability to either get a nice atlas, or to get a nice image of a part of the sky, or to study one object in very exquisite detail.
There's been nothing else that is so sensitive, so can look so deep into the radio sky and get images that are so sharp. It has already revolutionized radio astronomy.
Since LOFAR pretty quickly established antenna stations in several countries, we established as Astron the International LOFAR Telescope. That entity runs the entire facility to the benefit of astronomers around the world.
Since start of the operations in 2011, we already collected 35 petabytes of data. Only a small fraction of the data has been analyzed so far.
There are many processes that go on in the universe that emit radio waves at those frequencies that are very poorly explored. This starts from the sun, then on to magnetic fields in galaxies, black holes, back to the epoch reionization.
We already have many very interesting results. For example, we observed pulsars, fast rotating pulsars, but also the slowest rotating pulsar. We have the lightning data, so we actually see how lightning forms over the Netherlands.
We are looking at radio sources in galaxy clusters, millions of light years across, that are particularly bright at low radio frequencies, and they are produced by shock waves. These shock waves accelerate particles in magnetic fields, and nobody understands how that works. Before LOFAR came along, maybe 20, 30 sources were known, and now we are discovering them almost on a daily basis.
We're looking at the 21 centimeter hydrogen line, so we expect to see the cosmic dawn at the low frequencies, the low band antennas, and the epoch of reionization at the high band antennas.
At LOFAR we're also investigating sources of gravitational waves to see what astronomical objects have produced these events. Learn about magnetars, neutron stars, and very exotic phenomena in the universe.
LOFAR is a major facility, and as such it is always evolving to remain at the very top. For that we have just defined a major upgrade program that we have called LOFAR 2.0.
A major difficulty for low-frequency radio astronomy is the ionosphere. We want to make use of the solutions of the higher frequencies and use those calibrations to correct the data in the low frequencies. And the way we want to do that is to triple the hardware such that we can actually read out simultaneously high-band antennas and low-band antennas.
LOFAR, of course, is first and foremost a radio astronomy instrument. But at the same time, we want to make sure that our results have as much societal relevance as we possibly can. And that's where space weather comes in.
The LOFAR for Space Weather project is to form a separate beam to continuously monitor the sun or monitor the solar wind.
So far, LOFAR has been very successful in serving the sky between 100 and 200 megahertz, but pushing down to the very low frequencies will require LOFAR 2.0. There are going to be a lot of exciting things lurking in those images that we probably can't even think of. In LOFAR, we're just now preparing a release of data. In that portion of the sky, we've discovered 300,000 radio sources. Understanding that part of the high-energy universe, this is just one of the many aspects where LOFAR is going to break ground.
LOFAR at the moment is without a doubt the premier low-frequency radio facility in the world. And now we are taking great strides to LOFAR 2.0. That will be a fantastic instrument for early universe research, all the way close to home to space weather research. It's that enormous range that really excites me about LOFAR.
Scientists are trying to learn more about a mysterious, powerful cosmic ray. It's believed that they have traveled to the Earth from beyond the Milky Way galaxy. Cosmic rays are charged particles that travel through space and rain down on Earth constantly. For example, low-energy cosmic rays can emanate from the sun. Scientists say that the new energy of the subatomic particle is equivalent to dropping a brick on your toe from waist height.